So thank you very much. So as the title of this talk says, I'll talk about sublinear algorithms for approximating graph parameters. So let me start by saying what I mean by graph parameters. So basically, a graph parameter is any function that maps a graph to some value. And I'll talk about undirected graphs, so you can talk about directed also, and I'll talk both about weighted and unweighted graphs. So for example, you might want the average degree. That's like the most basic, maybe, function or parameter that you can think of. And maybe more generally, you can think of small subgraphs, and you want to count the number of small subgraphs that appear in the graph. You might want the number of connected components. And then you can think of optimization problems, so you might want the minimum size of a vertex cover or an approximate value of it, maximum size of a matching, number of edges that should be added to get a property, minimum weight of a spanning tree, and so on, so on. So I won't continue with more examples. So basically, for each of the parameters that I just defined, there are efficient algorithms. You know, and when we think usually about efficient, and with respect to graph properties, then we think, you know, polynomial-time algorithms. You know, at best, for some of them, there are linear-time algorithms. You know, what more can you ask? So, I mean, in this audience, then definitely kind of the jump that I'm going to make is not so surprising. But maybe the context and purpose I'm presenting in this way, because the context of thinking of graph algorithms, usually we're still used to thinking of efficient being polynomial time. And here, in some cases, as you know, you may think of, the inputs may be very large, and we might want even more efficient algorithms. We'll want sublinear time algorithms. So kind of connecting to what was discussed in the panel, so it's not that I think of the graph that I want to do something sublinear because I think it's harmful to use the whole graph, but rather it's a question of efficiency. So I want to trade off approximation with efficiency, and we'll see kind of more precisely what I mean. So these algorithms, basically, they do not read the entire input. So again, it's not that you get a graph, you work on it, you output something. They are randomized, and they will provide an approximate answer with high success probability. So let's be kind of, again, a little more precise in what I mean. So the algorithm is given query access to the graph. So what kind of queries I may want to consider? So one type of query is neighbor queries. So you can go to a vertex, to a node, and you can ask for its ith neighbors. So it's not that there's a meaning about the order of the neighbors. There's no meaning in the order. So either it can ask, say, for the first, second in some order, or it can ask for a random neighbor. So that's one type of query. I will allow also degree queries. You know, what is the degree of a vertex V? And a third type of query are vertex pair queries. Is there an edge between U and V? And just one comment, if the graph is weighted, then I'll get also, in the first and the third type of query, I'll get the weight of the edge. Now, in this talk, I'll focus about the two type of queries here. The type of queries you're allowed, you know, depends on the type of graph you're working with, its representation. So I'll be interested here in this talk only about sparse graphs, either bounded degree or bounded average degree. So the relevant representation will be incidence list, so I can get the neighbors of a vertex and the degree, but not necessarily I can ask about a pair of vertices. Usually there won't be an edge between them. Okay, so this is what the access that you have to the graph. And now what you want from the algorithm, after it performs a number of queries that is sublinear in the size of G, and sublinear can be, you know, square root of n, log n, or maybe will not depend at all, where n is the number of vertices. And what it should output after performing these queries is a good approximation sigma prime of sigma of G. That's the parameter we want to approximate with high success probability. Now, what do I mean by good approximation? I can think of several types of approximation. So probably the strongest one will be to approximate the value within 1 plus epsilon. So I wrote it in a non-symmetric fashion. Just for simplicity, you can make it, of course, symmetric. So that's one type. So the algorithm gets epsilon as a parameter, and it outputs 1 plus epsilon approximation. Now, sometimes this won't be possible, and we'll allow it. There will be a fixed alpha, let's say 2, for example, and there'll be a fixed alpha, and you want an alpha approximation, or maybe just a slightly more alpha plus something small. And the third type of approximation is maybe it seems a little less standard. We'll see when I talk about a particular problem. You'll see why it's a natural one. We'll allow both a multiplicative estimate here and also an additive estimate, and the additive estimate depends on the range of the parameter, and we'll see why this is meaningful in various contexts. Okay, so I'm going to survey, there'll be 4 parts of the survey, as much as time permits, and kind of in the order of the examples that I gave before. First, I'll talk about the very basic graph parameter of the average degree, and I'll talk a little bit about generalization to approximate the number of subgraphs. I'll see what I mean by it being a generalization. I'll talk about minimum weight of a spanning tree, also a very basic optimization problem that we might want to optimize the value. I'll talk about the size of the vertex cover, another very basic one. And again, we'll see if time permits, I'll talk a little bit about a different type of estimating the distance to having a property. So how many edges do you have to add in order to get a property, to estimate this value? Okay, so I'll kind of, in the first 2 examples, I'll give more details, and later on it will be kind of more high level, so you'll need to concentrate more in the beginning, but you can relax more as I go along. And maybe my goal is really to give you a flavor both about the type of problems that are studied in this context, and also some ideas. So even if you say, oh, but this particular one, that's not exactly what I'm interested in, I have kind of more complex type of parameters that I'm interested in, maybe kind of there will be these ideas that you can take home with you that the algorithms use, and some of them kind of appear more than once. So this is really what will be my goal. Okay, so we're talking part 1, average degree. So I'll denote it by, just a minute. Okay, so the average degree I'll denote by average, and I'm going to assume the average degree is at least 1. We can also do estimates when the average degree is smaller, but basically it means that there are isolated vertices, so really there's a subgraph that something is happening within, or several subgraphs. So let's assume the average degree is at least 1, and this can be extended. We'll have to pay more if the average degree is small. Okay. So let's start with the basic observation. So if we think of the average degree, so what we have like a function. We think of the degree as a function. To each vertex in the graph, there is its degree. And we want to estimate an average value of a function. We can query, we can go to a vertex, and ask what is its degree. And we want to estimate this average. So if we forget that it's a graph, we just think that it's a function, then we would be in trouble, because we have the range of the functions between 0 and n-1. And so a general function, if we want to estimate its degree well, then we would really need a linear number of queries, because there can be like very few places where there's a very large value, and everywhere else it's 0 or maybe 1, and then you'll have to hit those places in order to get a good estimate. But we're talking about not a general function, but a function that is defined by degrees of vertices in a graph. So we're going to exploit this non-generality of it being a function defined by the degrees of a graph. Okay, so first, Uri Feige showed that you can obtain basically a little more than 2 plus epsilon approximation of the average degree just by performing degree queries. So basically, you are querying the function on the value of the degree, and you can do it with square root of n over epsilon degree queries. So you get something sublinear, much less than n square root, and linear dependence on 1 over epsilon. And he also showed that if you want to go below 2, then you need a linear number, so you can't really do anything much better than simple, just asking all queries if you want to go below 2. But note here that I said that his algorithm uses only degree queries, while if I have access to a graph, I can ask neighbor queries. That was the type of queries that I allowed also. So with work with the dead Goldbach, we considered asking both degree queries and neighbor queries, and then we show we can go below 2. We can get basically, as good an approximation as we want. We'll pay for that. 1 plus epsilon approximation, and the dependence on n there's just another log factor. So if you know the tilde here hides a log factor. So, but it's basically roughly goes like square root of n, and there's a poly 1 over epsilon dependence on epsilon. So before I talk about it, I'll give you really basically all the ideas behind this algorithm. I'll just say 2 comments. So first is that when the degree, actually the average degree becomes higher, then you can get the complexity decreases. So if you have a high average degree, then it will be square root of n divided by the average degree. So this becomes better. And also, the results are tight. When I say both results, it's both the first one only with degree queries and the one with neighbor queries. And the results are tight in terms of the dependence on n over the average degree, so you can't really get something much better. Okay, so now let's see how it works. First ingredient. First ingredients, it's just a base ingredient that you use in various algorithms, bucketing. So I'm going to consider, again, in my head, I'm not going to do it, I'm not going to run over the whole graph and actually define this partition, but in my analysis, I'm going to think of a partition of all the vertices into buckets. So what is within each bucket, the number of buckets is roughly log n over epsilon. And in each bucket, the vertices have very similar degrees up to a multiplicative factor. So here beta is something like epsilon over 8. That's just a constant. And so the degree is roughly 1 plus beta to the I. That's in the I bucket up to a small factor of 1 plus epsilon, roughly. Okay, so now next thing we say, we kind of think we have this wishful thinking point of view, and later we deal with the details of how to do it. So what do I mean by wishful thinking? Say, just suppose that I could obtain, somebody would give me, for every bucket I, would give me an estimate little bi, which is roughly the size of the bucket. So again, it's roughly 1 plus or minus epsilon over something of the size of the bucket. Let's just suppose this were the case. Well, then pretty much I would be done, because then I would take this estimate, so I would take this estimate bi, sum over all the buckets, and I would, pressing the wrong thing. Sorry. So then I would just take the sum over all the buckets, use the estimate that I have of the size, the estimate of the degree in the bucket, take the average, and that's it. And I would have a nice estimate, and I could, stop working, and I could go home. Problem is, how do we obtain this BI? That was a wishful thinking thing. How would we obtain an estimate? So we say, how would we obtain estimates? That's our work. We sample. That's how we obtain estimates. So we sample and we apply a Chernoff bound, something that because we can do this independently and uniformly. Still, we have a bit of a problem. The difficulty is that for buckets that are small, so I want an algorithm that has dependence roughly like square root of n. But if a bucket is very small, so a bucket is much smaller than square root of n, then just in order to hit it, not even I'm saying about estimating its size, just to hit it, I will need the size of the sample I need in order to hit it will be much greater than square root of n, and I want to stick to the square root of n. I don't want to go much higher. So I have a problem with these small buckets that I want, that I can't hit them because they're so small. So now here comes the second ingredient. If you can't beat them, just ignore them. So basically, I'm going to ignore the small bi's. I'm going to take the sum over the buckets and the degrees, only over the large buckets. Those are those I can deal with. They're nice. I can sample and estimate their size. I'm going to take only them. And large will be roughly square root of n, a little bit smaller than that. Also depends on the size of the number of buckets. So now, if I take only the claim is, which I'm going to try and convince you like in an illustration. So the claim is that if I take the sum only over the large buckets, those are those that I can estimate nicely. If I take only this sum, so definitely I won't overestimate because I'm taking a partial sum, but also I won't underestimate by too much. I'll underestimate by roughly a factor of 2. So this is my claim here, and this is what I want. This is what I want to prove now. That prove roughly. Again, when I say prove here, I'm there'll be the details here that I won't go into, which are not that interesting, but the high-level idea hopefully will convince you. Okay, so let's remember, what is the sum of the degrees? So the sum of the degrees is just, so that's what I'm summing in this sum over the degrees in this 2 stars. It's just twice the number of edges. Okay, so if we think about it this way, let's look at this illustration. So I have large buckets. Those are all vertices that belong to large buckets. And I have small buckets, all vertices that belong to small buckets. So what edges contribute to this sum here? So, and small, again, I'm just, this is what my definition of small. Okay, so I have edges between vertices that both belong to large buckets. I have those that one is in a large bucket, one is in a small bucket, and I have those that are between both endpoints are in small buckets. So now these, the ones that between vertices that both belong to large buckets, they are counted twice, like as they should be, once from each endpoint. On the other hand, these are counted only twice, only from the endpoint that belongs to a large bucket. And what about these guys? These are not counted at all. But now what happens if we look at, we look at this, then it gives us this, the summation here gives us roughly a 2 plus epsilon approximation using square root of n over epsilon squared degree query. So where's the source of the error? Where's the epsilon and where's the 2? So the epsilon comes basically from the fact that there are those, we defined small buckets sufficiently small so that even if you know there's a clique among all of these vertices that belong to small buckets, there aren't that many edges. So the error that contributed by those that are not counted at all is small. That's kind of the epsilon. But then we have this factor of 2. We have this factor of 2 because of the fact that we really do not, we count only once the vertices that are between large buckets and small buckets, and this is kind of inherent in using only degree queries, because up till now I used only degree queries. Okay, so we got to this point. This is not as good as Fege's result, because he got something a little better, because it was more refined analysis. But you get the idea of where does the factor 2 come from, and this additive error of epsilon. So now let's see what will be the next idea. How will we go down below 2 and get a 1 plus epsilon estimate as we would like? So the third ingredient is basically, so we say, okay, there are those that are not counted. We already said, no, their contribution is small. We don't care that they're not counted. But we do care that the edges between large buckets and small buckets, they're counted only once, and there can be many of them. Actually, there can be, all vertices, all edges can be of that type. So we really want to do something about that. So the third ingredient is that we'll estimate this. So if there's something missing, we're going to estimate the number of edges that are counted once and compensate for them. So what do I mean by this? So this is the third ingredient. Let's look at this picture again. Large buckets, small buckets, and let's kind of focus into a large bucket. And so I look at the large bucket BI, so it has the edges that go to other large buckets, the vertices in other large buckets, and there goes those that go to small buckets. But this is something that we can estimate. Large buckets, we can hit them. So we can estimate for each large bucket, we can hit it sufficiently many times, and then we can look outside. Here we'll use the neighbor queries that we haven't used until now. We can use the neighbor queries to estimate how many edges go out to small buckets, and this is exactly what we're interested in estimating. So we can estimate the number of by sampling neighbors. This is what we need. By sampling neighbors at random from each large bucket BI, we can estimate the number of edges that go from the large bucket to small buckets. And we'll call this estimate EI. And again, I'm not entering here exactly the normalization. These are the details that I don't want to get into, but then we'll get by adding this estimate. So here, this was 2 star. This was what we had in the step before. That was a roughly factor 2 approximation. And we can get, if we add this estimate, then we can get the 1 plus epsilon approximation. Here now, the contribution, there are 4 sources of error. There is the fact that we sum only over small buckets. There's the fact that we estimate only each BI. We use only 1 plus beta I, which is not precise, and the EI. So there are 4 sources of error, but if we take beta to be sufficiently small compared to epsilon, we're done, and we got the 1 plus epsilon approximation. Okay, so in this first part, I said there was a subpart of this, which I'll just discuss on a high level, so you see that this kind of can be extended. So if we talk about approximating the average degree, it's really approximating the number of edges. That's actually what I said just in the last slide. So edges is like the most basic subgraph you can think of. So now, what about other subgraphs? What about slightly extending the notion of just estimating the number of edges? And in general context, it's known as counting network motifs. And in work with Milo Gunen and Yuval Shavit, we considered very kind of one extension, simple types of subgraphs, length 2-path, that's like one extension of edges, and more generally, S stars. So stars will have a center, and they're connected to other vertices. And note here that the interest in these type of small, simple object is that basically what they give us, if we know the average degree and we know something on the number of 2 stars, we can get the variance on the degree distribution. So we had the average, and we can get the variance. And if we have larger stars, we can get more information about the degree distribution, higher moments. That's one motivation for these particular types of structures. Okay, so what do we get? So if we denote by n sub s, that's a number of stars, of s stars, we can get 1 plus epsilon approximation algorithm. And now the query complexity, before I show the next equation that I was reminded by what Andre Border said today, that you shouldn't really use more than one equation in a talk, and I've used already several, but this one is really one that I would like not to have to use, but I'll carefully, I'll convince you of that you'll get a feeling of what this weird thing looks like. Before I tell you what this weird thing looks like, this is the complexity of the algorithm, let me just say that it is weird, but it's real. So what I mean by it's real, that actually it's tight. So it's not just an artifact of our strange algorithm, but it really is, the expressions that we have here, the terms here are for real. So that's, so now let's look at this a little more. So you don't really need to look at it, and what I'm going to do, I'm going first to break it to show you what is its structure and give an example for a particular S. So basically, this expression, there are three intervals of values of the number of stars. And all the important thing is that, if you look at this expression, it's not even clear that it's sublinear. But if you break it, you can see that in each of the ranges of the values of n sub s, it is sublinear. So there's a sublinear behavior, and it's kind of interesting that it starts by being getting better as the number of stars increases. Then in the middle range, it's just a fixed function, and then again it starts decreasing. So to be a little more concrete, let's look at an example of for s equals 3. So if we look at the first range, when very few number of stars, just n, we get n to the 3/4. That's sublinear. If we go to the middle range, then we get something like n to the 2/3. And I took it to an extreme when there are lots and lots of stars, but basically you can't have more n to the 4th, but if you have roughly n to the 4th, then you get a very, very efficient algorithm, just order 1, the expression up to the polylog n factors. So I think I'll just say that in general, I won't go into details of the idea, but in general I say that we use the bucketing idea, both for s equals 2 and more than that, but we need to understand better, so I'll skip this, I'll just say that we need to understand better the relationship between the number of edges that cross between different buckets. So while just for edges, there were small buckets and large buckets, here we need to understand the structure much better, but that's something I won't go into, and just want to show you the type of problem that we're interested here. Okay, so this was first part, gave you a taste of a type of problem and the type of way that we attack it. And let's go to the second graph parameter, also a very basic one, minimum spanning tree. So we want to estimate the weight of a minimum spanning tree of a graph. And I'm going to consider here graphs with degree bound, a maximum degree of d, and the weights will be integers between 1 and w. And Chazelle, Rubenfeld, and Trevisan, they also gave a 1 plus epsilon estimate of the weight of a minimum spanning tree. And they did it basically linear in d and w, and polynomial in 1 over epsilon. So again, sublinear does not depend at all on the size of the graph, only on the degree and the weight. And I'll just mention that the result is tight. And another nice thing is that it extends. I said maximum degree, but actually it extends to the average degree, so the graph can be sparse, but with varying degrees, and still we'll get a nice, and also the weights can be in a range. They don't really, the integrality of the weights is not important, it's just easier to describe. Okay, so here also I'm going to basically give you the idea of how the algorithm works. So first, let's start with a special case. Suppose that the W is 2. So the weights are either 1 or 2. And let's denote by E1 the edges with weight 1. And G1 will be the graph that is induced by those edges. So it's all vertices and only the degree 1 edges. And one more notation, C1 is the number of connected components. So so let's look kind of at the picture. If we just have two types of weights, what does the minimum spanning tree, the minimum weight spanning tree look like? So it looks like it has to span, so there are these little trees that span the connected components of the graph when you only look at the degree 1, the weight 1 edges. And then there are edges, heavier ones, that connect between those trees. Just think of running Kruskal algorithm for minimum weight spanning tree. So this is what you get. So looking at this, what this tells us is that really the weight of a minimum spanning tree is a function just of the number of connected components of that graph that has with edges of weight 1. Because what do we have? We have the number of edges of weight 2 are just those that connect between the connected components. So that's C1 minus 1. And the rest are of weight 1. So we get a closed expression of the weight of a minimum spanning tree as a function of the number of connected components. So then it says, okay, so if we want to estimate the weight of a minimum spanning tree, then we just need to estimate the number of connected components of this type, of this subgraph. That's all we need to do. Okay, this was where W equals 2. What about more generally? So more generally, the weights are between 1 and W, and we define EI to be the number of edges, the edges with weight at most I, and we define the sequence of graphs with growing weight. Then we can get an expression. So this is just for weight 3. We can get an expression for the weight of a minimum spanning tree that depends on the number of connected components of each of these subgraphs. So you don't have, we can do it as an exercise afterwards. Why this is true? Let's just believe that this is true. So now we reduce the problem of estimating the weight of minimum spanning tree to estimating the number of connected components of graphs. So let's look, so that's what we want to do. So kind of we made one step in understanding something about the structure of the minimum weight spanning tree, and we want to exploit it algorithmically. Okay, so now we have a graph H. I mean, afterwards we'll apply it to these GIs. We have a graph H. We want to estimate the number of connected components. It's denoted by C of H. So what will be the first idea? Let's kind of, in order to estimate this, let's assign to each vertex, let's assign a number, which will be the number of vertices in the connected component of V. That will be n sub V. So why am I doing this? Why am I giving a value to each vertex? Because now I get a simple expression, C of H, the number of connected components, is just the sum over all vertices. Each vertex contributes 1 over the size of its component. So now when we sum them together, if we bunch them, so think of there being, these are 3 components and of these sizes, and so in the component where there are 4 vertices, each one contributes a 4th, so together they contribute 1, and here these guys contribute 1 together, these guys contribute 1 together. So in general, I gave each one something like its part in the total contribution of the number of connected components, and together we get the total number of connected components. Okay, so this is all very nice, but what will I do with this? So we made a step, and then we just said something about an expression for the number of connected components. So now this reminds us a little bit, so what do we have? Again, we can look at this as a function. What do I mean? We have a graph. Each vertex has a value, which is 1 over n of v of that, for that vertex, and we want to estimate a sum. So again, how do we estimate sums? Okay, again, we would like to do this by sampling. We'll in order to estimate C sub h, we'll sample vertices and we'll compute n of v. how do we compute N of V? Well, N of V, number of vertices in my connected component. So I'll just do a BFS and find how many vertices are in my connected component. So here again, we have a bit of a problem. So sampling is all good and nice, but sometimes we have some problems like we had in the previous algorithm. Here the difficulty is different. Here the difficulty is if N of V, the number of vertices in my connected component, is large, and I want to do a BFS until I see all of them, that might be very expensive. There might be some connecting components that are very large, and this is very expensive. So again, we kind of use the same rough idea. If it's too expensive, then again, just ignore it. So what do I mean here? So here I'm going to define S will be a subset of vertices that belong to not too large connected components. So here, not too large. Again, I'll call it beta here. It'll be different, but the number of vertices in my connected component is not too large. And now what will happen here again, if we take the sum only over these vertices, we won't overestimate, but we will underestimate, but not by much. Because basically the idea is that if I look the number of the contribution of those connected components that are relatively large, the total sum of the number of them has to be small, because if they're relatively large, they're disjoint, there can't be too many of them. So now if we look at this, sum over here, then we get an error at most beta n, which will be good enough for our purposes for particular appropriate beta. So now basically we're almost done. The algorithm for estimating the number of connected components, it will select something. We'll see what beta is. Some number of vertices. As a sample, for each one it will run a BFS, but, so here's the point, that the BFS, it will run until it gets the number of vertices in my connected component, or it will have like a threshold. So if we go over N of V, if we go over, 1 over beta, then we stop. And we just ignore that. So that's like somebody that is not an S, somebody that belongs to a big connected component, we don't care about them. For those that do belong to small connected components, we'll take their sum in the sample, and from that we'll get an estimate of the number of connected components, and basically this will be the complexity. Now, why do we talk about connected components? Because we wanted to estimate the minimum weight of a spanning tree. So in order we will have to run this algorithm on each of the graphs, and if we set beta appropriately, in this case, if we set beta to be epsilon over 2w, we'll get what we want. But here, no, this will give us an algorithm with linear dependence on d, but higher dependence on epsilon than we would have liked and on w. And as I told you in the beginning, the Chazelle-Rubin-Trevisan got better complexity, but they're just by a more refined algorithm. So again, I'm giving you kind of a rough sketch of the algorithms to give you the high-level ideas without the precise details that can give something better. But this is basically the idea of the minimum weight spanning tree algorithm. Okay, so now as I said, we're going to be a little more high level, but still to give you like the ideas that are in each of these algorithms. So the third part is minimum vertex cover. So here this was initially considered in work with Michal Parnas. Again, we want vertex cover. We want a set of vertices that touch all edges. So again, a very basic combinatorial optimization problem, and we want to understand, can we do it more efficiently just by sampling, but approximating. That is roughly the idea. So here the first basic idea is, again, we do a suppose. We kind of in all of them, we first think, what would we have liked to have? And let's think how we'll do it. So the suppose is, suppose I had an oracle that for every given, I would give it a vertex, and it would give me yes or no, where yes or no, the meaning is, does it belong to the oracle in its head has some vertex cover. It's not a minimum vertex cover, but it's not much larger. It's alpha factor larger than a minimum vertex cover, and it would just tell me yes or no. So again, this would reduce the problem if I want to do something sublinearly, and I have such an oracle, then I would get an alpha epsilon approximation. I'll just remind you what that means. I could get a multiplicative factor of alpha and an additive error of epsilon n. Just by sampling, I would sample something 1 over epsilon squared. I mean, this choice is just so the Chernow bounds will work. And for each, I would ask the oracle, and then I would get the error would be the combination of the fact that the oracle answers according to a vertex cover that is not a minimum size, but alpha approximate, and the sampling error of the algorithm. Okay, so now the question is, and before I'll stop here and I'll ask you, okay, so this was all suppose. We said, suppose we had somebody could give us something, but how are we going to do it? So here comes the second idea. Second idea is to use distributed algorithms to implement the oracle. So what do I mean? In one sentence, what do I mean distributed algorithm? There are various models. Here I think of the message passing model. So in distributed algorithms, I think of there being on graph for computing graph parameters. In each vertex, there's a processor. And a processor in each round can send messages, and here I don't care about the size of the messages at this point, can send messages to all its neighbors and receive messages from all its neighbors. That's a distributed algorithm message passing model, and the main measure is the number of rounds. And what happens in the end, when the algorithm terminates, each vertex should know the answer to whatever we want to compute. In this case, it would know, is it in the cover or isn't it in the cover? In coloring, it would say, we know its color. So in different type of problems, the vertex knows in the end what is the answer for himself. Okay, so why distributed algorithm? Why does this help us in the context of our problem of getting this oracle for a vertex cover? Okay, so first, just actually, I'll continue with the connection with the distributed algorithm. So suppose I have a distributed algorithm for the vertex cover of some other property, and it works in k rounds of communication. So that is the measure of what in distributed algorithms. Then I want to say the following. Let's look in the center here. I have this is my vertex V, and I know that if I ran the distributed algorithm, after k rounds, I would know the answer for myself. So what does it mean, k rounds? In k rounds, I can get information only from vertices at distance at most k from me. So now what we're going to do, the oracle will simulate this. Oracle will say, okay, if I want to answer for a particular vertex, I don't care what happens in distance greater than k from my vertex. I'll just look at the subgraph, and I'll simulate the algorithm for the distributed algorithm for this distance. So what will the cost be? The cost will be the d to the k, the degree, maximum degree, to the number of rounds. So now the complexity will depend on how many rounds do we need in order to do this? What kind of distributed algorithms do we have? So here, luckily, there are, we can also find a special purposes algorithm for this, but there are algorithms that were designed for this purpose, for distributed algorithms. And what they showed is that it's possible, using distributed algorithms, we can get for C greater than 2, we can get C epsilon, so factor C multiplicative and epsilon additive with complexity that grows something like d to the order log d. So it's super polynomial, but still sub-exponential. And if you want to get to a factor 2 epsilon, then you need to do something. Then it costs some more. So before I tell you a little bit just about the progress on this problem, let me say again a few comments. So first is that we can replace, I said that working depending on the maximum degree might not be great because there might be vertices with very high degree, some with small degree, but we can replace in the expression, we can replace the maximum degree with roughly the average degree, so this is possible by modifying the algorithm. The second thing is, okay, we had C factor estimate, a multiplicative approximation, factor 2, what about going below 2? And putting aside computational efficiency, just the number of queries that you really need to see. So this is, you can't really, if you go below 2, it starts becoming expensive, and you have to depend on the size of the graph. So we'll stick to 2. And the third thing is, okay, so let's go in the other direction. What about allowing ourselves a worse multiplicative estimate, some factor C? So here, still there is a gap between the upper bound and the lower bound at this point in time, but still the average degree is really the right. You can't go below the average degree, whether it's a high average degree, small average degree. You can't go. That is really what we have. This estimate is what is this value of the average degree is what is holding us from. That's kind of the lower bound bound that we can't go below. So there have been a sequence of improvements for, if we stick to 2 and epsilon, there have been a sequence of improvements. So the first one was also used a distributed algorithm, but got something somewhat better, a different distributed algorithm, and got something somewhat better. Still not polynomial, but sub-exponential. And then there was another work that was, on one hand, it wasn't really better in all parameters, but it was different, and that was important. Sometimes it's not necessarily that you'll do something better, maybe sometimes you do something different, and in some cases it's better, but it's a different idea. So Nguyen and Onak gave it a totally different, not depending on distributed algorithm, but different idea of just emulating a well-known classic greedy approximation algorithm, and they got something that dependence on epsilon is slightly better and on d is not better. But the important thing about this is that this led to the next step, that jump from exponential dependence on d to just polynomial dependence on d, using the same idea of the algorithm but doing something more sophisticated. And then the last result was relatively recently, where we get something that kind of is almost tight in terms of the dependence on the average degrees, and we get something almost linear and polynomial in 1 over epsilon. And here, as I said, I'm kind of in this stage, I'm being relatively high level. I'll just say that there have been various other types of related optimization problems that have these sublinear approximation. The dependence on the degree varies depending on the problem and on sometimes there are assumptions for particular restricted graphs. So I'm not going over this in detail, just to give you a flavor that there are other types of other properties that have been studied. Okay. So. Okay, but so, and in the, okay, and that's just, so then I'll get to just the last part. Here mainly, it's really, as I said, I'm getting kind of fewer and fewer details. And here, mainly I want to give you kind of the type of parameter is different from what we had before. So we had average degree, which is very basic, average, counting number of subgraphs. Then we had optimization problems. We want to estimate the value for the optimization problem. And now it's a different type of here I want to talk about parameters that are the number of edges that you need to modify in order to get a property. So what I mean here is, if I have some graph property, say connectivity or k-connectivity, something that you really want to know about your networks. And so we would like to estimate the fraction of edges that need to be added or removed in order to get the property. So this is a different type of, it's like, how many corrections do you have to do in order to get a particular property? And the fractions with respect to the number of edges you have. So you have, like, if you're very heavy, then we allow you more. If you're light, then so it had to be compared to the number of edges that you have. And it was studied for some implicit results, and then with and we looked at it specifically. So note that actually we already have for free, we have one result in this part, which we talked about before, and that is estimating the distance to connectivity. Because connectivity is just, in order to know how many edges you had to add in order to be connected, you just need to estimate the number of connected components. This we already know how to do. We talked about before. So we have already one result here. So that's one thing that we already have. And I'll mention, without talking too much, that if we talk about dense graphs, so up till now, and I said almost all the talk was only about sparse graphs, but if we talk about dense graphs, so there are many edges, and we allow to ask queries of the form, is there an edge between a pair of vertices, then there are some known results that transform to distance approximation. For example, you can estimate the number of edges that have to be added in a dense graph to get a large cut. So this sounds, remember, this is a hard problem related to max cut, but here we can do this type of estimating the number of edges that need to be added in a dense graph. This is something that we can do very efficiently. And there are also some general results of Fisher and Newman that actually can transform algorithms of one type. That's another type of thing that I thought I'd talk about in this talk and thought it would spread out too much, which is property testing algorithms. So all algorithms for which you can actually just decide whether they have a property or are far from having it, can be transformed to get distance approximation. So this is another type. And here, maybe in the very end, I'll go back to sparse graphs, which is what I talked about before, and I'll just kind of say a little bit about the type of properties that we can deal with. Then for sparse graphs, there isn't a general transformation, but there are particular for different properties that were studied. There are results, and as I said, k-edge connectivity is really, you want to estimate how k-edge connectivity says something about how much your network is robust to failures of edges. So here, if you really want quickly, you don't want to run something, you don't want to run an algorithm, flow algorithm on the whole graph, you just want to get an estimate of how far you are from being k-connected, then this can be done in sublinear time. So I won't go exactly, I'll just talk about what are the properties, and there are various other, say, cycle freeness. You want to know if the graph is close to being a forest, being Eulerian, being triangle free. So there are various results with various qualities of estimates, and again, kind of using some of the ideas we talked about before and some other ones. So this is just kind of more details about the results that we get here. So to summarize, what did I talk about here? So I talked about sublinear approximation algorithms for various graph parameters, and the importance here again for me is that I would have liked to run on the whole graph, that I would get something perfect if I did that, but I have limited resources of time, so I want something, and I think the graph is very large, so I just, I can't afford reading it all, or it would take me too long, so here comes kind of the sublinearity. The importance of it is really being something very, very efficient, and I can afford an estimate. So I have randomized approximation algorithms that are very, 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 very efficient. And we talked about average degree and number of subgraphs, minimum weight of a spanning tree, vertex cover, and I just talked a little bit about the notion of distance to having a property. And the ideas against sampling, of course, comes. It's all based on sampling. But then the question, what do you do with what you sample? What do you do with what you cannot sample? So here we saw an example. If something is very small, in some cases, you can just ignore it. It's not always the case, but in some cases, it is what we saw here. And the question is, how do you combine the knowledge that you got from sampling in order to get the correct estimate? Thanks.